The following content has been provided by RWTH Aachen University.
All right. Good morning, everybody. Welcome to Designing Interactive Systems 1. Today, we're going to jump into the next part of the topics that Norman covers in his book. I'm going to expand on those a little and give you our own flavor of those principles. Before that, a real quick review of what we talked about last week to jog your memories. First thing up, we talked about Gestalt laws. So I'd love to see if somebody has an idea of what Gestalt laws are basically for. Like, what do they fundamentally express? What is their fundamental point? Anybody has a little blue hand for me? Yeah, I know, this is like you just started and already you're asked to participate. It's tough. Okay, Aparna, go ahead.
So Gestalt laws basically tells us how people make sense of their surroundings, how people basically perceive things visually, and it's more concerned with how types are put together. If something is similar, we kind of think all belong to one another.
Exactly. So how people perceive things as belonging together, as belonging to a group. And you already gave one example when things are close together. Tejaswini, want to give some other examples maybe for laws that you can think of?
You want me to name any one of the laws?
Yep, a couple more that we can.
Yeah, so we have closure. So you can, like if the shape, if it's closed, like if there are lines that meet together, so you assume that it's forming like a closed shape. So like that's
Correct.
what the user perceives.
Any others? Victor, maybe?
Yeah, we can add the law of good shape. So we tend to remember better shapes, and simple ones, squares, triangles, rectangles, and so on.
Yep. Jasper, got another one?
Yeah, we got the law of experience. So if we see a shape and it kind of reassembles some shape we already know, we connect it to that shape and remember as this shape.
Exactly. And interestingly, so far you guys have skipped around almost the easiest to apply and the most direct applicable to user interfaces. Billet, what's your one?
Law of closure. Closed lines appear as groups.
We had that already.
Oh, okay. Sorry.
But thank you.
Okay.
Another one? Billet, you can still pick another one if you have another one.
Law of similarity, maybe. I missed.
That's been covered too. Okay. But we haven't heard one yet.
Law of common region. Did we have that? Sorry, I missed the beginning of the class.
We did not. We did not. So what's the common region one about?
Common region is the bounded areas. We see the bounded areas when the regions appear as belonging together.
Right. So in particular, if something is within a region or a closed shape, inside it, the things that are inside it or on a similar backdrop, for example, those appear as belong together. And interestingly, we still haven't heard, I think, Amit, which one are we missing?
Law of continuity.
Yes, we've had that. What's that about?
Yeah, actually, if we have a continuous shape or continuous line, it seems together basically. So.
Right, and I think we still haven't covered one. Not sure we heard proximity yet, did we? So just moving items around and grouping them close together versus spaced apart, the law of proximity, that's kind of the one that is the easiest to apply really in a user interface, along with similarity, just making things look similar if you want them to belong to a group. All right. Then we wondered how we can compute information content in user interfaces. So what's the information content of a toggle button, for example?
A toggle button has 1 bit, so it has like 2 options.
Exactly, 2 options. Log 2 of that is 1 bit. Easy for those kind of discrete examples. It became a little trickier when we were looking at information content in analog scales. How do you measure the information content of an analog scale? We can't express it in bits, really, at least not for our purposes, because then we want to understand what about this, Fabian?
We kind of want to figure out how many states the average human can perceive, and then we can try to measure it in bit again, but that's not really accurate.
Exactly. It's accurate as far as you can. You can't compute it theoretically. You have to run an experiment. But if you run it with enough people, you get an average value. You're right. It's going to be more of a distribution of values along different kinds of people that tell us how many levels people can reliably distinguish. All right. And we had a long discussion about analog digital scales, the pros and cons. I'm not going to go into that. You remember the heated discussion that we had last week on that topic. And then we looked at the Swedish hairdryer. What were the key problems, or what was the key problem that you could summarize most of the things we talked about so far about that hairdryer? You can summarize under one fundamental principle that Norman also talks about early in his book. I'll give you guys a few seconds to raise your hand, apart from our usual suspects. Otherwise, I'll pick one of the usual suspects. Or I might pick a random person. That's also always fun. Marta, go ahead.
Well, the main problem was that we didn't know how to communicate with it. We didn't know how to turn it on, or how to just increase the speed of it. And I guess the signifiers maybe weren't visible for us.
Okay, so I love the expression, I'm trying to communicate to my hairdryer. That's interesting. We would probably, with a hairdryer, I would probably say I'm trying to just use it, or operate it, or interact with it. I haven't been talking to my hairdryer lately, but yeah, thank you. So you rightly pointed out it was hard to figure out how to turn it on and how many levels it had on those kinds of things. And there's one term that Norman gives to all these different problems. Victor, what would that run under? What do you think?
Yeah, actually, we had a problem of visibility. So there was lack knowledge in the world. We don't see how we can basically use it. We need to know it.
So the visibility is the fundamental issue. And remember, there's visibility of the current state, like is it on or off? Right? I think we have a picture here. Visibility of the current state, visibility of the available states, like what other levels are available, like what speeds, as you said, and how do I get there, right? What are the right actions to get to those states? Those are all not clear from just looking at it. And it's a fairly simple device. It shouldn't be hard, right? It should not be something that needs to be discussed and guessed about. And we did a little bit of a better design, which actually had to do with signifiers, as you pointed out, where you place the signifiers, the different labels, the labels for what levels are available, to put the labels next to the little control and move the control up and down. All right, and then finally we talked about the conceptual models. And how is the conceptual model that a designer has of a particular system, how is that related to the conceptual model that the user builds of that system? How are they connected, and how do they relate to each other? That was towards the end of the class. Yeah, Lucia, go ahead.
I think it was related in the way that the actual thing has to invoke this more or less the same conceptual model with the user than what the designer had in mind when creating it. Because if the user has a different conceptual model of the item, then the user doesn't really know how to use it or uses wrongly.
Right, that's correct. And I want to clarify something here. Maybe that came across wrong. Let's say you were to write, you know, the Windows Explorer or the Mac Finder, right? Now you as a computer scientist know that there are, you know, weird things going on in the depth of the operating system, you know, with file and directory handling and all that kind of stuff. And that is not the conceptual model we're talking about here. When you are an interface designer, an interaction designer, a UI designer, then you have to think of an illusion, right? We talked about the magician, right? You have to think of a layer that is consistent in itself, that has, well, I won't say it has nothing to do with what's going on underneath, but it doesn't need to reflect the thing that is going on underneath. It has to be its own consistent image. You know, the image of friendly little yellow folders, right, that we know from the Windows Explorer, for example. And that is the conceptual image that you as a designer have to formulate. You have to think of this. And it has to be an image that you think your users can understand. You can't say, well, I have a perfect conceptual image of how the Unix file system works. There are those nodes and files and IDs and whatever. That doesn't make sense, right? That's not the image you want to relay to the user. The image you want to relay is one that you have to come up with as a designer. And then you, once you know what that image is, you cast the user interface, you make it work so that it creates that image, that illusion. And that has to come across to the user unchanged, right? That has, I just want to make sure that that's clear. It's not the technician's expert image that we're trying to force into the user's head. That wouldn't make any sense. It's actually an image that we want the user to develop that is appropriate for what we can expect them to know and understand and how to apply the thing. Right, so great. Everybody should be awake now, hopefully jogged a few of your memory cells. And we're gonna go on to mappings today. We're gonna talk about mappings and a few other concepts from Norman's book. First of all, mappings, you guys all know from your mathematics lectures, you know that mappings are a relation between elements from two different sets, right? For example, a function is an example of a mapping that takes maybe a real number to another real number, like the x-square function. That would be a very mathematical mapping. We're also talking about relationships here when we talk about mappings, but not in the same mathematical sense. What we mean with mappings are relationships mostly in two directions. They either go from an input device, like a control, like that light switch that you see up there, to the real world. For example, the lamp that turns on, right? That light switch turns on. Or they can go from the input device, like the joystick you see there on the right, to the virtual world of what's happening in game with, you know, your race car as you control that joystick. So this is one direction, right? From devices, input devices or controls, as we like to call them in HCI, to the world, which can be real or the virtual simulated world of a game or an application. And then the other direction is the output direction, where you have the real world, for example, the temperature inside a liquid container that gets, or, you know, it could be your body, you know, that gets indicated on a thermometer, right, on a temperature scale, and that scale is a display, right, of some sort, some output device that shows that value. So it takes a real value, a real measurement, if you like, or a real state, and shows that in the interface as an output device. And the other situation there could, of course, also be if you have, let's say, an MP3 player running in the background on your laptop, and that MP3 player has a display to show you what the volume settings are, then it's going to render that value that's running inside the software on a user interface component as well, like this volume meter that we're seeing there in the diagram. Okay, so this is what mappings are. So far, mappings just exist, right? They're neither good nor bad. They just are something that always exists when you create a control for something, an input device, or when you display an output, when you display a value or a process in an output device. Now, good mappings are natural mappings. And I will explain more about these on the following slides, but just to give you an overview, Good mappings are always natural, and natural can be expressed in a couple different ways. They can be analogies that work spatially, where the spatial movement or arrangement is similar between the, for example, the control and the real world. They can be perceptual, where the whole thing, the whole control looks like the real world thing, or they can be biological, where it basically, for every person on this earth, it immediately makes sense to have the mapping in this way. Or they can be cultural, where it works for a particular part of a culture or a particular part of the human population. For them, it is basically perceived as, yes, obviously this is the right way to display this value or to control this value. If we use these natural mappings, then we have a couple of advantages. They are usually understood immediately. Nobody actually has to think twice about them. Well, they actually don't have to think once about them, honestly. They just intuitively are operated in the right way. People often talk about intuitive interfaces, and it's a really overused word. But if you use natural mappings, I think this is one of those examples where you can really say the user's intuition leads them to doing the right thing. This also means that they are easier to remember, of course, so you don't have to spend as much time learning them. If you do them right the first time automatically, then you never really spend any conscious learning effort, they just work. And they also then, by being easy to understand and easy to remember, they enable better ease of use. All right, so what are these natural mappings? Let's go through each of these in order: spatial, perceptual, biological, and cultural. The first one is actually the easiest to understand. It is also the most common one. Spatial analogies are going to be given to you in this example here. Let's assume you are the interface designer for this car lifting platform here, right? That's used in a car workshop. And I've made a little arrow here pointing to this panel on the side. And let's assume that you can design this panel now. You can design what this panel for lifting cars up and down on this platform would look like. What would you do? What kind of controls would you create for this platform? Just raise your hand if you have an idea. Yeah, Sam, go ahead.
You would use 2 buttons, one for up and one for down.
Mm-hmm. And how would you arrange those 2 buttons?
The one for up, you would let it be upwards, mm-hmm. and the other one downwards.
Okay, so not like this, I hope. I think that's what you described this, right? Yes. The up button above the down button. Exactly. So here, see, as a user interface designer, you immediately do the right thing, because even to you, this is so logical, right? If I have 2 buttons to move this platform up and down, I'm going to place the up button above the down button. But spend a little time looking around your real world surroundings. Look at your alarm clocks or devices that you find oftentimes that have buttons for up and down functionality. More often than not, you will find that these things are not above each other from your point of view, but actually next to each other. And then every single time when you look at them, you kind of have to look at them, look at the labels on there. So they have to have signifiers, or you have to kind of think hard at the way they were arranged. And it's always a little bit of a mental effort that you need to spend. That is completely unnecessary if the designer places the device, the controls for this in the right way. All right, so this was fairly easy, right? Up and down above each other is a spatial analogy to the movement directions of the car itself. There is, however, and this is a question for sort of the mathematically inclined, it would be an even better mapping, an even more intuitive sort of one-to-one mapping of the car's position to a user interface control. Does anybody have a different suggestion here? I think Alisava, go ahead.
Yes, hi. Sorry, I have one notice regarding the previous slide like this. car things. As I work in different industries, like manufacturing industries. Mostly these kind of things have the safety issues. Like when it goes down, it can have some damage for, let's say, for some employees. This is why regarding button down button should be somehow encapsulated with some notion. Let's say, how could I say it? Like, you know, this emergency buttons with the glasses, like it should have some control of in some level, like, because after some point, it can bring some damage for humanity, let's say.
Right. So, for example, it could be a button that is sort of inside a recess, so that I have to actually poke inside, so that I don't accidentally lean against it and press it. Right.
Exactly. Yeah.
Good. Thank you for bringing that up. I was actually going to get to that question of safety in just a second. I'm going to revisit that. I just want to see, does anybody have a suggestion for ignoring all questions of safety here, for an even more intuitive way to control it? How about Rachel?
Maybe a lever.
Exactly. So more something like this, right? Where I kind of move a lever up and down on a sliding scale or something like this. And basically the moment I move the lever here, the car sort of moves with it, right? That would be the perfect natural mapping. Because what we have right now with the up and down buttons is actually sort of a first derivative of the position, right? And this is something that digital devices do a lot, because buttons are cheaper than sliders in production. And so a lot of controls are done as buttons. And what that means is that you have to press that button maybe several times, or you have to press it for a certain duration. And by doing that, you slowly change an actual value. So mathematically speaking, the button is actually the first derivative of the value, right? I change it by a certain amount rather than actually setting it to the value that I want. Be aware of that. And that's one of the reasons why alarm clocks are so annoying, when you have to keep holding a button to increase the value. And then, you go over the value and you have to go back because you kind of missed the point where where you would have to let go of the button to stop the counter again. So these are interfaces that immediately introduce a time-based component into the UI. And as Marcel and Oliver know, I just have this whole personal thing going with time-based user interfaces that have these timeouts built in. I can always get very, very annoyed at these. So this is a very simple example, right? Even that button where you hold it, and then while you hold it, the car keeps moving, you have to pay attention for a specific amount of time. And it's usually going to go either too slow and you wait and you wait and you wait, or it moves too fast and then you have to backtrack, right? It's really hard, almost impossible to get these time-based interfaces right. Okay, so the lever is the most natural mapping, because I could move it quickly to the top if I know I want to go all the way to the top, or I could move it very minutely in small increments. But now, of course, the comment that that you just made about safety totally applies, right? Because in the morning, let's say, the boss walks in and he leans against the console and he kind of like pushes that lever down with his elbow accidentally, and his assistant was still lying under the car trying to fix things. It's going to lead to a lot of paperwork, right? And a lot of mess to clean up. So from a work safety perspective, this is not the best design. I totally agree. And I would even go as far as you were saying, even the down button will have to be somewhat protected so that it doesn't get pushed too easily or accidentally. But this is the work of the designer. You have to balance certain considerations, right? So work safety can be something you need to pay attention to, and it often means you need to make certain things a little harder to use than they naturally would be. But I just wanted to point out that from a usability point of view, this lever would actually be the better mapping, the best mapping between the car position and the control. Maybe the best one would actually be, maybe I could just put my hand onto the car and push it up, and it senses that there's a force being applied, and then it magically, servos start moving it up and down, something like that. So I can feel like Superman lifting a car with my hand. That would be another really nice natural mapping. Matthias, you had a comment. Go ahead.
Isn't another problem with the lever idea that it breaks more easily if you have this machine for, let's say, 10 years, and these buttons are really robust, but the lever could one day have problems.
Yes, agreed. That is another concern. Long-term reliability of components. It's going to be more expensive to create a lever that will be as robust and as long, long-living as these buttons. And in dirty environments, it's much easier to build a well-sealed button, for example, than a well-sealed lever. Absolutely. So good, you're thinking like designers, right? You're applying these different considerations. Just make sure you don't forget the usability consideration and make it part of the equation when you look for solutions. And accept that in an ideal world, the best usability solution would be the one to use. And then there may be other factors that move you away from this optimum usability target, but you should at least know where the target is, so that you know consciously where you are stepping away from it. Right on. Okay, so this is the rule, right? When you can, ideally, you arrange controls in the same way that their real-world counterparts or effects are arranged, right? So the real-world counterparts, for example, if there are lights in a room, one is in the left part of the room and one is the right part of the room. And as I walk into the room, there are two light switches next to each other. I want to make the left light switch turn on the left light and the right light switch turn on the right light. That's kind of obvious to do, right? And still, it often isn't done, right? Oftentimes, you wouldn't believe how long we had to talk to the people, the electricians who were renovating our lab here, until we had explained to them how we want our light switches arranged, because obviously we wouldn't want them, like in a stupid way. So we had long talks with them to explain to them why we wanted them in a particular order. They have no idea of this concept of natural mappings. Another example is a car stereo. So if you have, for example, a car stereo where you can fade the audio from front to back, ideally, you would want a slider that moves from front to back, right? And that, however, is almost, it's basically impossible to position in a normal dashboard. So normally it's mounted somewhere in front of you. And if you're lucky, it's an up and down slider, where you then can somehow map up to the front and down to the back of the car. We'll get to that later. But if it's a left and right slider that moves things from front to back, then it becomes very hard to remember which one is which, right? There's no natural mapping between left and right and front and back in your car. I should also say, so, I mean, if you have the ability, if you have effects in space, of your controls, and then you can arrange the controls in the same way that the real-world counterparts are arranged. And it works the other way around too, right? If you have to display something in an interface, and the things you're displaying have real-world counterparts, then you also should arrange the display in a similar way. Now, sometimes you can't do this, or I should say there's another option, for example, for room lighting and stuff like this, which Norman calls activity-centered controls. And these are becoming more popular. What I'm talking about is, for example, when you walk into your living room and let's say you have two settings for it. One is like a watch a movie setting, where you basically turn the lights off, you turn the projector or your TV on, and you set your volume to medium. And then there's maybe another one, the party mode, where you have like, colorful lighting going, your projector is off, your volume is turned up to full, and maybe the aircon is working on full power. These don't have spatial mappings, right? They then control several devices around the room in a single setting, kind of like a scene, if you want. And this is something that doesn't relate to spatial analogies. If you do these activity-centered controls as a designer, though, you have to be very careful, because they can be catastrophic if you don't design them carefully. For example, we have a room that we normally teach this class in, and in this class, we normally try to dim the lights so that we can show a projection. But after a while in that room, the lights automatically turn back on because they detect movement in the room, I believe. And so it's trying to do the right thing for the current activity in the room, but it's not smart enough to do it well. And then it's super annoying, right? So a lot of these smart home technology or smart technology is often more like a smart ass technology that is, trying to make things right, but is actually guessing things wrong most of the time. All right. I have another example here. This one blew my mind. I went to Heidelberg. I went to the new clinic years ago, and I entered the elevator to the clinic building, and this is what I saw. Okay, I have a couple questions for you. The first question is, how many floors do you think this building has? You can just post your answer in the chat if you want. That'll be a lot of chat messages now. Okay. I'm hunting for my little, there it is. Let me take a look. Lots of messages. Okay, we're seeing anything between 2 and 100. I love it. And 9. No, did I see 9 there? 9 is very interesting. Okay, so that's ridiculous, right? We are actually discussing how many floors there are. Again, it's just an elevator. Should be easy. I'll give you a hint. It's actually just 2. So, next question, which way is up? If you think, 99 is up, then enter 99. If you think 00 is up, enter 00. Okay, at least with this, we have almost perfect agreement. Almost everybody is saying 99. You are all wrong. Congratulations. So in fact, 00 is not where the toilets are in this building. It's actually the ground floor. And 99 is the first floor underground because this building goes into the ground. And so I don't know what the guy who mounted these plates was smoking when he did his job one morning, but I can only guess as to what was going on. He probably just he wanted to put a -1 in, right? He wanted to put a 0 and a -1 in, and then he had forgotten the negative numbers in his little toolbox, to install the elevator. And he was like, oh crap, I forgot the minus digits. What am I going to do? And he went through his collections like, here's the 99. Let me see. If I add 1 to 99, I have 100, and I only have 2 digits, so the 1 kind of drops off to the left. So maybe then it's 00 again. I don't know. I'm rationalizing now, right? It's like I don't know what he was thinking, but that's the only thing I can imagine that still lets me believe that there is some sense in this world. So this is a terrible design, right? That's really terrible. Now I have a challenge for you. I mean, it's clear he should have put 0 and -1 in there, right? Then everybody would have known which way, which thing is where. But you've learned other things in last week's, or actually in the mapping lecture just now today, and I want you to redesign this interface, even if you only have these buttons available. How would you improve this interface? Okay, we got the race of the Fabians. I'm going to call Fabian Friedrichs.
Okay, first of all, I would put the buttons above another so that the floor that's lower is below the button for the floor that's higher. Yeah, the mapping makes so few sense that I actually forgot what button goes where. And it would also put the buttons for opening and closing the doors above one another, and I think that should improve visibility of what arrow points away from the middle, because right now it's kind of confusing. You can't really get it with one glimpse. We have to actually look at it for a few seconds to also know which button does what. I don't know if that works, but I think that might improve visibility for those buttons also. So I would put those buttons maybe on the left side, and the number buttons in the right order of the floors on the right side.
Okay, right. So good idea. Visibility is probably not exactly the right term here for what you were describing, but clearly arranging putting the 00 button to the top and the 99 to the below it makes, of course, for a natural mapping, right? Because then the lower floor is the lower button, right? That's obvious. And putting those two open closed door buttons right beneath each other would actually align them with the center line underneath each other, and that would sort of lead to your eyes more easily perceiving the similarities and the differences between those two buttons. There is something else, and this is sort of the bonus question, and now you have to think back to last week's lecture. If you do it this way, if you do it this way, that you put the 0, 0 at the top, 99 at the bottom, and the two buttons for opening and closing underneath each other, you are actually improving the interface with another principle at the same time. Which one is that? I think I saw Selena raise her hand.
Yeah, you would also benefit from the law of proximity, because the buttons that are above one another, they are closer together. So
Exactly.
they would be perceived as a group.
Exactly, right? So if you look closely, those two buttons here are closer to each other vertically than the left and the right group are to each other. And in fact, once you put the buttons above each other for 99 is here and 0, 0 is above that, for example, then it doesn't matter what it says on those buttons. It could be apple and orange on there. I would still probably press the right button if I wanted to go up and down. Right? So that's how strong these natural mappings are, that the signifiers become really sort of secondary in usability. Wonderful. So thanks to the clinic in Heidelberg for this wonderful interface. Here's another one. This is my old stove that I used to have at home. And you can see here the mapping between these controls here. These are the four controls, and the four plates are arranged, in the typical order of in a square, basically. So we've got an issue, right? This is not a natural mapping of the controls to the actual plates. And because of that, the manufacturer placed little icons next to each of the four dials. So adding labels to the design, which is an indicator usually that, a design may be improvable. And the best thing in this one particularly is I can see that when I'm standing like a meter away from the stove, but once I step up to it and actually use it, the labels disappear, right? So they become kind of useless because I always have to step back and stoop down and look beneath this little ledge to see, okay, what was the label again? Yeah, okay, so let me continue my job here. So not a great design. Let's talk about this stove topic for a second here. We already understand that the key thing that's wrong with this mapping is that it's not natural, right? But if you think about it mathematically, this arrangement of 4 buttons in line actually creates 4 factorial different possible arrangements that could be right? Because each of the 4 buttons could actually relate to each of the 4 different heating plates, right? Now, we can assume that these heating plates are split left and right? So these 24 possible arrangements of 4 factorial get reduced if you assume that the left 2 buttons are going to belong to the left 2 plates and the right 2 buttons are going to belong to the right 2 plates, because otherwise it would be really a devilish design, right? It would be evil. But that still leaves us with how many different arrangements? How many do we have left now when I assume that the left 2 buttons belong to the left group and the right 2 buttons belong to the right group of heating plates? Any ideas how many we're left with? Oh, lovely, no blue hands, so I can call somebody up. How about Lucas? There's a Lucas there.
4 possibilities then.
Yeah, 4. Easy enough, right? The left can be 2 possible arrangements, the right can be 2 possible arrangements, and that gets factored with each other, multiplied with each other. So what that means is we do need labels, right? So, and that, as I said, indicates a bad design. Now your challenge is, how can we do a better job? What are better solutions? If you have an idea, just raise your hand. Yeah, Sarah Sahabi, go ahead.
Yeah, hi. I think I would have oriented towards the reading direction. So I would start it with the upper left circle and position it with the left button, for example.
Mm-hmm.
And then I would have gone to the right, probably, but that's actually the opposite of what you said.
Okay, so you would, okay, so I need to explain what your freedom is, okay? So the 4 plates are at the top of the stove, and you have the ability to change the controls around a bit. You can rearrange the blue controls. So the 4 stove tops stay the way they are. So what would you do? In that case, you know, doing what you just said would be sort of, you know, not very intuitive, right? But you can rearrange these things a bit. Yeah, Fabian Reiners, the other Fabian.
Yeah, so if we have like unlimited space, we could just like copy the image so that we have like one in each corner. And if there's too less space to do that, there's actually a way my oven does it. It's like this, you can see it. Like 4 circles, and they're like a little bit shifted up and downwards. It takes not a lot of space, but actually you will immediately understand which plate is which button.
Good. And why do you know which one is, for example, the lower left button, the first button? Why do you know what that one refers to?
It's because it's like left and down, so it couldn't be any other plate. And the other, the left one that's up, it's like shifted a little bit upwards, and it's still on the left side. So
yeah,
I don't think there's really a way to misinterpret it.
Correct. The 2 left ones belong to the 2 left plates. But and you're perfectly right. But what's interesting is you're actually applying a rule here with natural mappings without anybody noticing, right? It's so obvious that we don't see it. Do you have an idea what's going on? Because the two controls are arranged vertically, right? They're above each other, and the plates are behind each other.
We are like mimicking the location. If we like relate to the location to each other, so they are like in the same way, but not exactly on the same places. It's like if you look at one plate and look at another plate, they are still in the same direction from each other. I don't know how to really express
so
it.
that's what's going on. What you're describing is your controls are vertical, right? They are right here, and your plates are here. But since you're looking down onto the plates, in your field of view, the rear plates are actually above the front plates, because that's from your angle of looking at them. So if you take the projection, if you would take a picture of it, like I did in that other slide there, then you would actually see the rear plates above the front plates. And that's why the mapping of putting the rear plates above the front plates on your front plate makes sense. It's the same mapping because of that way. If you somehow were cooking while you are crouching under your stove and it was like made from glass, you could look up to your plates, it wouldn't work, right? But you know, that's not how stoves are built. Okay, so we got a couple solutions here, right? In fact, the middle one is a little confusing. I'm going to get to that. The first one is you could actually, as you said, like just mimic the layout in 4 buttons at the front to the 4 buttons at the top. And then we would have this, you know, from our perspective, these 2 mappings would, you know, map to each other, these 2 arrangements would map to each other naturally. The second one, I think, Marcel, although we need to change that around, that's not quite right, because the orange one, the 4 orange plates would still stay in a square arrangement, but you would make the 4 blue dots be arranged the way that we arranged the 4 orange ones here, right? So that's kind of similar to what Fabian was just showing, just with a centered projection rather than an off to the side oblique projection. And of course, another way to do it would be if you had the option to place the controls on top of the stove. Some stoves do it that way, right? They actually put the dial right next to each stove plate, and that uses the law of proximity to tell you that the control is close to where the stove plate is. But that has other issues of like keeping them clean. When you spill milk on your stove, it's going to run into the control and it gets sticky, and you might bump against it with your pot as you move things around. You might burn yourself if you try to control it. So it has other issues. But all of these are better than the default arrangement. The only advantage that the default arrangement has is that it can be done in a very narrow front plate, very narrow height, because all the 4 buttons are arranged in a line. But it really makes it hard to see things. So even just a slight indication of this sort of perspective view would help people a lot to turn the right plate on and off at the right time. And that is actually a safety concern, right? You want to make sure that people don't accidentally turn on a plate they don't actually want to use. Right. Artem, you had a question?
No, I just want to ask the third variant. Maybe it's not so good because when you're cooking and you have some boils on your plate, you can control if your plate is on or off, and so you have to check from each side.
Yeah. Good point. Good point. Yeah. So it also creates issues of sort of occlusion where you wouldn't be able to maybe see the controls.
Yeah.
Right. And again, we could talk for hours about stove design here. My goal is not to design the Perspex stove. I wanted to point out what the role of a natural mapping is in this whole design discussion, and that you can apply it sometimes without spending too much extra, money for the design or making other things too much more difficult, and actually improve usability quite a bit. All right, so that's spatial mappings. And we're going to move on to perceptual analogies. This was the second kind of analogies that I pointed out. If you have, by the way, if you have more questions or comments, feel free to keep shooting them into the chat, and Ollie and Marcel will get to them. Perceptual analogies, as the second kind of natural mapping, actually take the UI, take this natural mapping even further. So in this case, the UI element, for example, the control, the input device, is actually an imitation of the real world thing you are controlling itself. A wonderful example right out of Norman's book is this car seat arrangement that's mounted inside the passenger door in Mercedes cars that actually looks like a tiny seat itself. So if I want to, move the backrest forward, then I know exactly what to do. I just push the little tiny backrest forward, and sure enough, the actual backrest is going to move forward that I'm sitting in, or the other passenger is sitting in. I like to call this the voodoo principle, because it's almost like sticking needles into a voodoo doll to hurt a real person. So that little plastic car seat model here is sort of the voodoo doll for the actual car seat. You're doing things to the control that then have the exact same effect in real life. Okay, another way of arranging things is what you could call biological analogies. And with biological analyses, I mean things that everybody on this planet will perceive in the same way. Oh, Artem, sorry, did you have a question, or do you just need to lower your hand? All right, good. We're still seeing your tiny blue hand, so just if you can lower that, thanks. So let's do, too fast. Let's do a little in-class exercise here. I would like you to call up, to mention a few measurements that you can think of that you may want to control in, for example, in a physical process or in an interface. And I'm going to just take these and put them write them on 2 little pieces of paper here, and we'll see what the arrangement then is. So what are examples for measurements or things you can set in a user interface? You can just, actually, why don't you just post some into the chat? It's going to be quicker that way. And I'm just going to monitor the chat window a bit and see what's coming up there. Okay, fan speed, temperature, thank you. Temperature. Speed of the fan. What else? The control of flow. Okay, volume. the amount of CO2 in an aquarium, okay. Battery power, yes. Humidity, light level, amount of flame in a stove, or like how high it's turned up, yep, okay. Interestingly, a pH value, somebody definitely has an aquarium here. Amount of water from a faucet, yep, okay. All of the ones that you mentioned so far, tire pressure, all of them fall into one and the same group. They all fall into what we know as, it's called additive dimensions. What additive dimensions means is that they are all dimensions or measurements that everybody agrees that there is a more and a less. For example, if you wonder, is there more or less temperature, speed, pH value, battery power, CO2, you know, heat on your stove or pressure or something like this, all of these map into a more or less, right? We all agree what's more and what's less with these. So that's called an additive dimension. You know, you can, these are things you can increase or decrease, and everybody agrees about the direction. Second challenge is type something into the chat where you think it's a dimension that is not additive, where there's no universal agreement of more or less. Color, exactly. An on-off switch, that's debatable. Taste, I love that. Yep. You know, so the saltiness would be an additive dimension, but taste for itself, like is it sweet or sour or bitter, for example, is not additive. These are dimensions that are called substitutive dimensions, where different values substitute each other without being added or subtracted, right? And then there are things that we can debate. For example, an on-off switch, you could argue on is perceived as more than off, for example, if it controls a light or anything like that. And so for an on switch, you would typically say, even though it's only two values, so it's a discrete value, typically the on state is more than the off state. Although there might be particular situations in which you might interpret that differently. It depends on what the switch is controlling. Loud and soft volume, I would argue, is an additive dimension. But if you go for the pitch of a note, for example, there's actually not universal agreement on what is up and what is down, what's more and what's less. Some people say a higher pitch is more than a lower pitch. Others say, no, the higher pitch is thinner and the lower pitch sounds more voluminous, you know, like from a bigger source. So they interpret that as more. And then luminosity, I'm guessing you mean light color there? Or Victor, can you explain what you mean with luminosity particularly?
Yeah, I mean whether you see, I think we perceive differently how bright it is in the room. So that's why it's not clear whether it's brighter.
Okay. But everybody might think that the current level of brightness is maybe, you know, that seems high or that seems low, but that's not what I'm talking about. I'm talking about when I change the brightness, everybody will agree that now it's more or now it's less.
Oh, I mean, you mean dynamically. Okay, got it. Mm-hmm.
Yeah, yeah. So changes are perceived as this is more or this is less universally, and that's an additive dimension. Okay, so we got a lot of them here. So, you know, water level, heat, volume, line thickness, brightness, weight, all these things have an agreement for additive dimensions. For substitutive dimensions, we do not have these, right? Color, the audio pitch that I mentioned, or taste, or location, for example, is also one, is also not one that you can clearly arrange. And my point here is, whenever you have a dimension that is an additive dimension, you should always strive to put the controls for more and less, or the display of it, in a vertical arrangement. Because everybody agrees that more is up and less is down. For example, for water levels, for temperature, you know, we see it with thermometers. You would not normally see a thermometer where the colder it gets, the higher the number rises on the thermometer, or the indicator rises. And so if you find an additive dimension, think about the dimensions you're displaying or that you let the user control. Think about if they are additive, and if they're additive, think about if you cannot do a vertical arrangement to create a natural mapping where people will never get it wrong, right? This is another argument for the car adjustment, that you put the up button at the top and the down button below that. Okay, Fabian, and then Victor.
I only have one question. You said usually you should arrange them above one another, but I see a lot of volume sliders, also a lot of very good interfaces being from left to right.
Yeah, we'll actually get to from left to right in just a second.
Okay. Because that was like my question. I see this a lot of happening a lot of times with all of those scales, but volume in particular is often going from left to right. Okay.
Yeah,
but
definitely.
Then
No, you're absolutely right. Because what we're using for these biological analogies is actually this sort of top and bottom thing where nobody disagrees. But left to right is actually something that is more cultural, right? If you take the order of things, so for example, if you want people to read 3 things in order, or look at 3 signs in order, or operate 3 controls one after the other, if you place them top, middle, and bottom, pretty much every person on this planet will agree to operate them in that order. But left to right, obviously, is not as universally cultural applicable, right? For example, if you have a language that writes from right to left, in this culture, left to right is not the natural order of arranging things. This is really something we're only trained to in our writing system, because we write from left to right, we read from left to right, and so we assume that left to right is sort of a natural order, right? In Hebrew, it would not be. So left to right is not a biological analogy that applies to everybody, although designers often think it is. It is actually a cultural analogy that you can really only apply if you know what culture your interface is being deployed in. And here's here's another sign that you guys hopefully all learned in traffic school, that actually is quite tricky to interpret and to understand how it works. So when you look at the sign, there are a couple things happening. First of all, the most important one is we see a vertical sign, and through the cultural background knowledge, knowing that in Germany we drive on the right-hand side of the street, we associate the right-hand side of this with our own traffic lane and the other side with the opposite traffic lane. What's supporting that as well is the fact that we see the sign as this, but mentally, if we tilt it flat, so to say, it would still work, right? Because if you look down at the street, the cars that are, further away are also going to be up in your display, in your vision, and when they get closer, they get lower, right? So because we're looking down onto the street, so the vertical mapping of the sign maps to a horizontal mapping that we apply to it. So we kind of lay the sign flat in our minds, and it's only at that point that we can start understanding for sure in our culture environment that we are meant to be the right track here, and the other one is the opposite track. And then we apply another cultural convention, which is that red in our road sign language typically means forbidden, don't do something, and we then associate, hopefully, if you paid attention in traffic school, we associate with that okay, so we are meant to actually keep it slow and let other people pass first before we go. But there's a lot of things going on in this, if you think about it. So this is an interesting sign, because if you turn this upside down, for example, you know, you will see that it actually then seems to suggest, oh, okay, so now does that mean I can go first? Right? So there's several interesting mappings going on here that really only work if you're part of a culture that knows we drive on the right-hand side, and that knows that, you know, red is meant to indicate danger. Let me show you a good example for a biological, for applying this biological analogy principle to redesign an interface that's actually originally done quite badly. If you take a look at this ticket machine here, I'm sorry, again, it's in Stockholm. I don't know, I have something going with Swedish design here. But this ticket machine, if you had to operate it, you had to look at these many signs and explanations here quite carefully, and then you would understand that you need to do the following. You first start in the middle, and you press the blue button 1, 2, 3 times to tell the machine if you want a ticket for zone A and B, or A, B, and C. Then you have to move down and press the second blue button, once for a regular ticket or twice for a reduced price ticket. Then you have to swipe your credit card on the top left side of the machine. Then you have to move back to the center and press the green button once. And now the actual ticket appears here to the left, right? So this clearly needs labels, right? Imagine as a tourist, you come to Stockholm, you see this machine, you're going to be lost, right? You're just going to give up. So it needs lots of labels to make this work. And even with those labels, it's still really hard to use. So this is the labels, by the way, that then, you know, as you can see here on the right-hand side, this is the labeling that they add to it. And so it tells you, oh, number 1 is down here, number 2 is here, 3 is up there, and 4 is back down here. And still people obviously, you know, fail to use this. And knowing the principle of biological analyses, you could really make this much easier, right? You simply rearrange. You say, okay, the first thing you need to do is, you know, pick your zone. And then second step is pay your money. And the third one is get your ticket. You know, picking your zone and selecting your discount would be sort of in the first zone here. And that would be everything. And by the way, the one at the top there is a button for, you know, press for speech. So you would get, you know, an audio interface for people who cannot see, for example. But that's a simple way to rearrange this and have a top-down flow that people would feel much more comfortable using and would have much less trouble with. But just as an example, you know, this is an example of a display of stock prices in China, where you can see as things go above a certain level, they are drawn in red, and as they go below a certain level, they're actually drawn in green, which is not what you would expect if you come from a Western culture, but that just goes to show that, you know, colors have different meanings in different cultures. And then finally, mappings don't work in isolation, right? Mappings always help us to operate something, but we build conceptual models based on mappings. And I want to give you an example here. You all know when you're driving in your car and you need to turn on your indicator light, your blinker, right, in German, and you want to turn right. Which way do you push your indicator light lever? You push it up, right? At least if it's mounted the way that it's mounted here in this example. Why is this? This is not a natural mapping per se, right? Up does not map to right. But why does this mapping still work? Why is this mapping still easy to remember? Jesper, go ahead.
Yeah, because if we want to make a right-hand turn, we will steer to the right eventually. So we just put it up. So that's what we're gonna do next.
Yeah, you're right. And I think it's again an example of, it's so intuitive to us that we don't actually notice the ingenuity of the design. Because what if that lever had been on the right-hand side of the steering column? Would you still push it up to go right? No, right? If
No.
that, yeah, exactly. So the point here is that because your left hand in this case that is on your steering wheel, so this hand goes up as you make a right turn, it means that actually you are trying to trying to go right. You move the steering wheel up, and it's natural just to take the lever and pull it along for the ride, basically, as you turn the steering wheel. Right? So that's why this mapping makes sense to us. So we actually build conceptual models whenever we use something. And if the mapping is natural, it's just so much easier to build a good conceptual model. But if it's not immediately natural, like in this case, we build a conceptual connection to it and understand it. There's a wonderful example that Norman talks about for an indicator light on a bike, on a motorcycle. So on a motorcycle, when you turn right, there's a little switch that you push forward on the left-hand side of the handle. And the argument is the same. If I turn right, I have to move the left part of my handle forward to make a right turn. And as I do that, I can then push the indicator light switch in the same direction. He said this never made sense to him until a friend explained to him once what the mapping is, and then it's easy to remember. Okay. And so conceptual models, we always create them. We always make sense of things that we see. And if the mapping is natural, it's easier. But if it's not, then we tend to make ourselves a bridge with our conceptual model. And then, of course, in some cases, it's just totally messed up. Like this picture of an elevator with buttons where I don't have an answer for what was going on here. I don't know. It's just hilarious. Okay, so to wrap this up, we've got some design principles already here. We've got discoverability from last week, right? So you need to be able to discover the current state, the available states, and the actions that should be easy to determine. We should have a good conceptual model that we relate through the system image. It's consistent, its operations, its results work the same way, and the user then gets a coherent model in their head of how the system works, coherent with what we intended to put into the system image from our designer's conceptual model. And we employ good mappings. So we employ natural mappings between actions and their results, between controls and their effects, be it in the real world or in the virtual world, and between the state of a system, again, maybe a real world system state or an in-app simulated system state or length of a document, whatever, anything inside the app, inside that virtual world of our application, and the visualization of that in the interface. So that all helps us to create a better interface. And finally, when people do actually start with actions, we provide feedback about these actions, right? So when I turn on something, a light turns on, I should see that I have turned it on, I should see what current state my hairdryer is in, for example, when I operated it. So feedback is sort of closing the loop on this, but we're going to hear more about feedback later on in this class.
Yeah, so the question is regarding like if we think more is up, down is less. So I just come up with the idea with a submarine. So when you try to go deeper, so should you press down button because you think that you go deeper, or is the distance from the like the height decreases? Like what should I press?
That's a good one. I think for a control to go up or down in the water, you still want it to be mapped to up and down in the natural way. Because imagine yourself, you're at some kind of depth and you say, oh, I need to go up a little. I mean, you even use the word, right? So I think it makes perfect sense to say, if there was a lever to move the submarine's depth up a little, then it should be the button should be above the one that moves it down.
Okay.
Where this gets a little more interesting, if you've seen, Das Boot and all these like submarine movies, of course, the indicators, especially the old analog ones, are these round dials, right? So they actually have not really a natural up or down mapping. They have a circular mapping, and they often indicate sort of increasing depth as an increasing value to the right. And there you could wonder, is that the right way to show it, or should maybe be, you know, being at the surface be the maximum, and then going down, it should go down to more depth. But you know, that's also because the circular indicators are not natural mappings in themselves. They just basically are the next best thing we can do, and they partly just exist because mechanically it used to be easier to build circular indicators than linear indicators, right? Just because the mechanics of it are simpler to do.
But here I would assume that this depth, analog display works the same way as a speedometer. So if it's more depth, so it goes to the right. So here I will use already derivative from this mapping because I know how the speedometer works.
Yes, that's true. So the speedometer is sort of a learned mapping, if you want. It's maybe a cultural analogy, you could possibly call it, because we've seen it so many times in all kinds of indicators and valves and mechanical processes that we're used to it. You know, although, like I said, there is really in the digital age, there is no reason really to show things on a, you know, circular moving scale anymore, because it was just a mechanical reason that was easier to build. So if you don't need to show it, I mean, you can still use the convention in your interface, in your virtual interface, and people will be able to build on it. But who knows how long that's going to stay around? You know, 50 years from now, maybe people are like, why are you using a round scale, right? Doesn't make sense to me. I've never seen a real one in my life. We're now going to move on to constraints. Constraints are kind of like the evil twin brother, you could say, of affordances. They work quite similarly. If you remember affordances showing us what actions are possible, then constraints are things that limit the actions that are possible. So they limit the ways in which an object can be used. What that means is, by doing that, they actually provide a good cue for the proper course of action, the things that you should be doing, especially in a novel situation or an unusual situation. A good example is, graying out a function in a menu if there is no window open currently, right? Then you cannot do certain things, and so that menu option gets grayed out, so you cannot select it. That's an example of a constraint. The goal of constraints is to avoid errors in use, right? To avoid people making mistakes, but by keeping them sort of on the right track in the interaction, if you want. And the second effect of these constraints is that they actually minimize the amount of information that you do need to remember. So by doing these two things, they help you use the product, the system in the right way. Again, like with mappings, there are, like with natural mappings, I should maybe say, there are certain types of constraints that can be applied. We're going to talk about the four here: physical, semantic, logical, and cultural constraints. Let's start with physical constraints first. These are, again, the simplest form that you can most easily recognize. They rely on the physical properties of something, like the shape or size of something, to constrain the actions that are actually possible. One example would be if you have a modern, security lock on a door, and you got a few keys on your keychain, and one of those keys is like an old school key with an actual sort of, traditional shape, then you will immediately recognize that this will never fit into that lock, and you won't even consider trying it, right? That constraint keeps you from trying out the wrong key for that lock. On the other hand, if you have 5 safety, security keys, and they all kind of look the same, that constraint is not working because you can't recognize it. It's a bit like with the affordances. If you can't perceive it, it doesn't work. If the constraint is visible ahead of time, then it's way more efficient and more useful, right? So, for example, if you have a car key, let's say, and it's shaped in a way, like let's assume this is actually my bike, but anyway, it doesn't matter. It's a key that looks like it would fit in both ways. It doesn't have any kind of particular shape that suggests to go in one way or the other. Then it better also should actually work both ways, right? There are some really evilly designed car keys that look like they almost look symmetrical, but they only work one way. And of course, half of the time when you step up to the car, you put it in, man, I have to put it the other way around. So that's bad design, right? And I think we have all seen examples of that more than enough. If you've ever used the famous traditional USB interface, we've all been there where we take a USB plug. It looks similar enough from both sides that you try it out one way and then like, oh man, and then you have to turn it around, right? You really have to peer like into the connector to see whether it works. That's terrible design, right? The original USB connector is a terrible design because it looks symmetrical, but it isn't. The USB-C connector is a much better design because it looks symmetrical and it actually is. So you can put it in both ways. Okay. Here's another example of a physical constraint. What happened was one of our students, Simon, built made a test together with a PhD student else with a camera overnight in our space, and that camera needed the light to stay on. So what the student did is he took a metal bar, like a little metal angle bracket here, and put it over the light switch, taped it to the light switch, and so he added a label to it: do not turn this light off. But he also created a physical constraint that would actually avoid you to turn off the light, right? Just to make sure that people get it. Next up, semantic constraints. Semantic constraints are a little more subtle. They actually rely on our knowledge of the situation and the world to constrain possible actions. So no longer is there a physical barrier to doing what we want to do, but if we look at it and think about it, our meaning of the world basically tells us, that's why it's called semantics, tells us that it doesn't make sense. The example Norman uses is in a model plane construction kit. There's only one meaningful location for the driver's figurine, in the front, right behind the windshield, and facing forward. Even if it fits in different ways physically, it doesn't make sense. Notice that these things tend to be timed, right? They may stop making sense in the future because our meaning of the world evolves with technical and other advancements. So here are the two puzzle pieces that fit together physically but don't make sense, are still a constraint, but it's a semantic constraint. If you use these semantic constraints, just like with the mappings, you have to make sure that they work for your user population. So don't use a semantic constraint that won't make sense to part of the user group that you are trying to design for, especially across different cultures. And thirdly, and I'm really sorry, my PhD students years ago used a really old picture of mine for this wonderful example. And we never got around to replacing that. The logical constraints here are things that rely on logical conclusions to constrain the possible actions. So what that means is if you have that model plane construction kit, you know that in the end, it's logical to use all the parts in the kit, right? Or that you would perform a task in an obvious order, 1, 2, 3, right? Or that, if that is from this picture that puzzle is probably not complete yet because there's a piece missing, right? It's a little different from the semantics, but it's related. Take a good look at how Norman explains these two if you need more information. In fact, natural mappings often employ these logical constraints. So for example, that the left switch belongs to the left lamp is on the one hand a natural mapping, but it's also sort of the logical way of doing things. So you will find that constraints are often just sort of a different way of looking at natural mappings or affordances. So don't be surprised when you find that different concepts apply to the same situation. Finally, cultural constraints change over time and are things that generally lie on accepted cultural standards to constrain the possible actions. For example, if you get a package and you don't know which way is up because nobody marked it for you, but it needs, it may be important to be put the right way up because there's something fragile inside. If you look at the labeling on the package that's printed on the package from its making, then this often already indicates to you which way is up, right? The labeling doesn't even have to say up. It could say, Microsoft on the packaging. If it's printed in a certain direction and you read it, then you will deduct from that that this is probably the way that it should be held upside. But of course, this only works if you can read the writing, right? If it's written on there in a font or in a writing system that you are not familiar with, where you don't even recognize if the writing is upside down or not, then it won't help you. Similarly, cultural constraint of red equals stop is also, of course, only working for you if it's actually something that that applies to your specific cultural group. So, and this is, by the way, a root problem of universal design, of globally universal design that is just always going to give you trouble because many of these things that do rely on cultural constraints won't work in a global setting. And these days, we're often developing things for a global market. Okay. So let's do a quick exercise because these constraints are sometimes tricky to get examples for. I would like you to just spend a few minutes to think about a few examples for objects from your daily use and from your environment where you think that constraints are in use to help use them correctly. If you can, then try to find examples for different types, physical, semantic, logical, cultural. And some sample areas that you can think about are kitchen appliances. They often have these things, or security devices, or tools, or vending machines. And if you have an example, I'll just ask you to raise your hand, and I'll call you up to give me your sample story.
So with micro SD cards or SIM cards in phones, you always have these you can put them in and they're exactly shaped like the SD card of a SIM card so that the contacts are exactly in the right place for the phone to use it.
Okay. So SIM cards, great example. They've got this cutoff corner, right? That tells you that it will only fit in one direction. And so that would be a physical constraint, and it's also clearly visible if that edge is cut off, so you can determine it ahead of time. Okay, and similarly with like SD cards and stuff. Good. Fabian, you got another one?
Yes, I would actually think about the old antenna cables for TV. I think there's probably more than just this as an example, but they don't go both ways. You cannot plug them in the wrong way because they have different physical connectors. Nowadays, this is usually solved by using the same connector for whatever cable, USB-C, Thunderbolt, and having it actually work in software. But back in the day where this wasn't really a possibility, you often had different connectors. I actually witnessed a family friend once plugged in two computers and connected them with a VGA cable, and obviously one broke. So back in the day when software implementations to solve this weren't a thing, you often had different connectors.
Absolutely. Yeah.
Natural constraint.
Good example. These different connectors, especially if they are shaped sufficiently differently that you can clearly recognize them, then they will tell you almost without instructions, you can assemble something just by plugging things in where they fit, right? That should be, that's usually a good way to do it. Yeah, Aparna, go ahead.
I actually have one for physical and one for semantic. So the switchboard, the socket where the plug should be inserted, I would say that kind of feels like a physical constraint. Only 3 plugs which can be inserted over there. And coming towards a semantic constraint, I would think, especially in user interface designs, when a button is clicked for a particular process, let's say you want to delete something, you kind of disable it so that the user doesn't click multiple times. Or if something is getting saved, you kind of disable closing of that particular window. You try to at least give a hint to the user that some operation is going on, so don't click again. So that could be probably perceived as a semantic constraint.
Yep. Both good examples. The first one is interesting, especially I think where the physical constraint in plugs is really starting to show is you sometimes have, for example, the US plugs have this ground connector and the 2 live connectors, the full size ones, and the ground connector is a little longer so that you can make sure that that always gets connected first before you plug in the other ones. So it even suggests a certain order of doing things, which actually we'll come back to in just a minute with forcing functions. And the other example of having a button disable while it is not useful, for example, while something is saved, yeah, that's definitely, well, you could argue whether you consider that semantic or physical, because if I disabled a button and I cannot click it on a user interface, you could even say, well, I'm actually physically making it impossible, right? Our point was that when I have a logical constraint, for example, or a semantic constraint, I could physically do the action, but my mind is keeping me from doing it. Whereas a physical constraint literally disables the action for me to do. And you could argue that a button that's grayed out literally disables that function to be available, to be selected. It's not trying to explain to me that I shouldn't do it, but it actually doesn't let me do it at all. Okay. Oh, sorry. Yeah, Fabian Reiners.
I'm actually not 100% sure if it's semantic or logical, but if you look at component cables, there are like 3 different colors on one cable to plug in a device to your TV. And obviously you have to put in the parts to the matching color.
That I would consider a semantic constraint, I would say. Yeah, it's kind of similar to the the puzzle pieces. Okay, Alisava.
For me, just interesting regarding the fingerprint locking system. Like it starts with the button, and afterwards, like in iOS devices, it starts with like that, and afterwards they try to add it with the haptics, like vibrating things. And now new Android devices even has no any button, but like you are clicking it, and somehow display is making some feelings that you are unlocking the phone. I just wanted to mention this one. Like how the feeling is changing, like the unlocking or locking the phone, let's say, or systems.
That's definitely changing the process of doing that. But I'm still looking for the link to the constraints. Do you think there is a constraint at work here?
Like in iOS devices, like the finger style button, maybe. I don't know. I just like think about that.
Yeah, probably not such a clear example for it.
Yeah.
I would say in the interest of time, we'll move on. If you have more examples, feel free to post them in the chat. Marcel and Ollie will take a look at it and comment back on if there's anything to be clarified. this is constraints, and now onto forcing functions. Forcing functions are an example of sort of extreme physical constraints. They're known from safety engineering, and they are designed to help avoid errors, right? So whenever you do these, you are definitely putting a burden on normal operation, right? You're making operation harder. An example is seatbelts, where, you know, if your car doesn't even start without you putting the seatbelt on, let's assume that was the design, then, you know, it would create a strong physical constraint. But it would also mean that if there was a reason why you couldn't put on your seatbelt, maybe because, you know, the seatbelt is stuck or something, then you would actually avoid people using their car. That's why usually you can still turn on your car, but you just get these super annoying beeping messages that you know, that keep reminding you to put on your seatbelt. Another example is these stairways into basements here, where you have a gate. When you run down the stair because there's a fire in the building, and you are at the ground floor to leave the building, then at that point there's often a gate, especially in the US, to keep you from running down, continuing running down the stairways and ending up in the basement, where you may not be able to exit the building as easily. So that you usually have to open up in normal use and go through. So it's a hassle for normal use, but it's, you know, keeping you safe in case of a fire. This is also the first example for the first type of forcing functions, which Norman calls lockouts. Lockouts are there to prevent a particular action, like, you know, entering the basement, for example. Lock-ins, on the other hand, prevent you from prematurely stopping an existing action. An example would be when you today, you know, when you press power off on a device like a computer, it usually comes back to you and gives you a confirmation dialog, etc., and asks you if you want to save any data. So it's no longer a hard switch. So you cannot actually normally turn off your computer directly, right? The normal on-off functionality of, like, your laptop keeps you from doing that to avoid data loss. And if you want to override that, you have to go through a specific sequence. And finally, interlocks are there if the design focus is on ensuring a particular sequence of events. For example, when you have a microwave and you want to make sure that the user first turns off the microwave and then opens the door, typically microwaves are designed so that if you do open up the door, it actually leads to the microwave turning off at that moment. A wonderful design that I once read about was in a restroom, in a public restroom, where if you entered the restroom, closed the door, you could fold down the little shelf to put down your bag or something, or your hat or whatever it is. But when you folded down that shelf, it actually blocked the door from opening. So in order to open the door, you had to fold the shelf back up yourself. And in doing that, it made sure that people wouldn't leave things behind on that shelf, because people kept leaving things on that shelf when they left the restroom. And so this was a design that was trying to keep people from leaving their belongings on that shelf. Okay, so similarly to affordances, mappings, constraints, all these things, you will find sometimes it's difficult to ensure or to really nail down, is this rather a constraint at work of a particular kind, or is it an affordance at work of a particular kind? Oftentimes the interpretation is open to both. We are dealing with humans after all, with these fuzzy humans that are hard to pin down into a simple mathematical formula, and that's just the nature of these models, that they usually will work in more ways than one. The important point here is really what we're trying to give you are lenses, design lenses, so that you look at a problem from different angles and that you get a vocabulary to think about these problems. So if you know the concept of a forcing function now, you can think about situations and then reason about, should I put a forcing function here? And if I do, what is the effect on normal usage? Okay, with those in mind, Tejaswini, did you have a question? No? Or maybe yes? No, okay, good. All right, I'm gonna move to the 7 stages of action. This is another model that Norman talks about. Remember, we mentioned feedback earlier on, right? We said that we've learned some principles from the initial things like visibility, etc., and that we should also provide decent feedback. Now, this discussion here will go deeper into the question of feedback, and it will go deeper into the actual process in your head that goes on as you use a device, as you use a technology, as you operate a user interface. So the 7 stages of action is really trying to address the question of how do people do stuff? How do they interact with technology with their environment, really, on a very fundamental level? And the first model here is going to be just, well, we typically have a goal of reaching something, like I want to turn on the light. I do it. I change the world in the sense that I turn on the light and the light goes on. I look at the light. Did it turn on? I'm happy, right? That's a very simple overview of this cycle that we're going to look at. But we're going to expand both the execution part and the evaluation part into several steps now in the next couple slides. The reason for learning this is not just to understand how people do things, because we're not just, we're not psychologists. We really want to design well, right? So we want to understand why do people make mistakes, and can we somehow get a grip onto these different kinds of mistakes? Can we understand how they happen? Can we find a way to detect them and maybe correct them, or maybe even avoid them in the first part? So the 2 parts of an action of this, like executing the action to change the environment around us, what we call the physical world here, and evaluating what the results are. These are the 2 big parts of this 7 stages of action model. And it models this activity in a way that we expand each of these 2 sides of this large cycle into several more sub-steps. Let's first take a look at, assuming that we start with a goal, an idea like I want to turn on the light, for example, that we expand the execution side first. When we look at what people are doing as they formulate such a goal, like turning on the light, we actually have several sub-steps here. So from this, the initial formulation of a goal is often very sort of problem-centered. Then we sort of create a concrete plan to execute. That plan gets turned into an action sequence of physical movements, kind of like a robot control, and then we actually perform that action. Okay, so this is the rollout of this. Let's look at each of these in more detail. The goal formulation is often very vague and problem-oriented. Like I'm sitting there, I'm reading a book, and now I need more light. That's sort of very problem-oriented still. I haven't formulated that how I'm going to achieve that goal. I've just said that will be my desired end state, right? I want more light. That's where I want to get. I don't know how to get there yet. I just say that's where I want to be. And from that, I then need to derive a plan to get towards that goal. For example, I could say to myself, well, I'm going to turn over and operate that light switch over there. I'm going to somehow operate the light switch. That's a way towards the goal. Still in very vague terms, in general terms, nothing you could teach a robot, but it's a solution, right? It's not just a desired state, it's a path to that desired state. And once I have that, then my brain goes ahead and says, all right, I guess we need to formulate an actual sort of action sequence here, which I like to think of like, the commands controlling a robot, which is, okay, I need to turn around, stretch out my arm, and, poke that switch on that wall there. And from that point on, I then actually execute that action sequence and change the world accordingly. Right? So that takes us through this left-hand side of the 7 stages of action, from the goal to the effect on the world. Now notice that there is no one-to-one mapping from goal to the plan to the action sequence and its execution. For example, if, I don't know, if I'm at home, I'm reading, my wife's there too, I could also say, instead of turning on the light myself, I could say, oh dear, could you please turn on the light? You're standing right next to the switch, right? That's another solution that will lead to a different plan and actions, or that will lead to a different action sequence being executed, right? The goal is the same, the plan would be different. Okay, so now we've changed the world. We've done something to our environment, maybe just turn on a light, nothing revolutionary, but now we need to go through the evaluation. How does that work? Well, the first thing that happens, of course, is we perceive, right? Let's take the light switch again. You now see that, you are reading, and now you are perceiving a new level of light on the pages of your book that you're reading. You now need to interpret that. So you need to look at it and interpret whether that, what that goal means to you. For example, you might see, okay, this is now at a level where I can read comfortably. And then you compare what you've reached to your goal. What was my goal? I wanted to get enough light to read this text. Okay, I've reached that state. I'm done, right? The action, the 7 stages of action were run through completely and satisfyingly. So I have reached my goal by executing that. Put together, this left and right part gives us the 7 stages of action, as you will find them in Norman's book. From a goal through plan, specifying an action sequence and performing it, changing the environment, the world, and then perceiving the result, interpreting it, and comparing it. Now, in reality, these steps are actually usually hard to distinguish. A cycle can be event-driven or data-driven. For example, you run into a friend in the hallway at the university, and by seeing him, you are reminded that you wanted to actually talk to him about a homework assignment you wanted to do together. So you didn't set out and saying, like, I want to talk to this guy. The cycle started with you seeing him, perceiving him, interpreting him as your friend, comparing it to your current state, and then formulating the goal. Oh, right, I wanted to talk to you about something. So not all these 7 stages start at the same spot. The steps are in reality often not easy to distinguish, and complex tasks often include whole sequence of hierarchies or goals. So oftentimes you have a complex thing to do, and to do that, you need to formulate a first 7 stages of action model. And then after you're done with that, you then find that in one stage of your 7 stages of action, you actually need to go in and dig deeper and create a tiny little micro 7 stages of action inside that. We often also forget goals or discard them or change them as we go, right? So like I said, you meet somebody, many things are opportunistic or unplanned. You meet somebody, you talk to them, or the deadline of handing in the next assignment is the thing that gets you going, right? So it's not that you set out with a goal, but it's more like, the timer is ticking, and at some point you arrive at a certain decision that you need to now follow a particular goal. In general, these cycles can be driven by the world or by the goal. That's the understanding to have here. They can start by something that you notice at first, or by something you have in your head that you want to start with. Now, The 7 stages of actions are nice, but the real value of it comes from when we understand how things break down. And this is really interesting because you will understand different kinds of usability problems and how to distinguish them. It helps you to design new interfaces and interactions by just rethinking these breakdowns. And we call these breakdowns gulfs. Gulfs of execution and gulfs of evaluation. The first gulf of execution means I somehow fail in getting from my goal here through the execution path to my change of my environment. The gulf of evaluation, on the other hand, means that somehow between what changed in the world and how I perceived, interpreted, and compared it, I failed to get back to a meaningful outcome to determine whether I've now completed my goal or not. So it's the question of how do I interpret this state of the device, or how do I even perceive it, or how do I compare it to my goal? So the role of us as designers is to bridge these gulfs, to make sure they don't occur in usage. How do we do that? Well, gulfs of execution, and I'll give you some examples for that in just a second, you can usually get over with signifiers, with constraints, with mappings, and with conceptual models, with good conceptual models. The gulfs of evaluation are usually things that you can get across with feedback and also, again, with the conceptual models. Here's a very simple example. You get this bag of peanuts. Your goal is want peanuts, right? Want to eat peanuts, very, very sort of outcome oriented. Then your plan is, oh, there's a bag of peanuts. I guess I'm going to open that and eat some. And then you get to the action sequence, and that's where it gets tricky, right? So because this bag of peanuts actually doesn't give you a good indicator on how to open it, right? It's one of those bags where there doesn't seem to be any point where you can tear or open it. So the connection between your your idea, what you have, and actually getting there is not there. What's the problem? Well, we're missing good signifiers, for example, where to tear this bag, and good mappings of how we think about this bag. We might think that it should naturally open at the top, of course, and if that's not available, then we are in trouble. And there are several examples of this because the problem you might be facing can be that you don't even see where to start opening this bag, or there is this wonderful little red tab on the top of the bag, and you say like, oh, thank you, yeah, this gives me a clear signifier. This is how I'm supposed to operate this bag. I'm going to tear this red tab over and open it, and then you pull on that tab and it just rips off and the bag stays closed. We've all been there, right? All suffered through that. And that's an example where you had an action sequence formulated, you tried to execute it, but it failed, right? So it's a different level of where this actually breaks. So the gulf of execution opens up because there are differences between the actions that you plan and the actions that the system offers, which are the affordances that it has. And if that shouldn't be happening, then ideally, the system would let you execute all the things that you've got planned directly without any extra effort. That's the perfect world. I've got a wonderful little device here that shows this problem very clearly. This is a Bluetooth headset, and it has, apart from two buttons for volume, it only has a single further button, and that button is labeled mode. And I can tell you, if you find a button that's labeled mode, then you are usually already in trouble, because that's often an indicator for an interface that's going to be hard to use. Let me tell you what this button mode does. And I need to read this off because it's so hilarious. Based on what the state of the device is, and based on how long you press this button, it can do the following things. It can turn on the device. It can turn it off. It can be used for Bluetooth pairing. It can be used to initiate voice dialing. You can use it to redial a number. You can use it to cancel the current dialing. And here are my two favorites. You can use it to accept a call or to reject a call. And you can use it to hang up the current call. But hey, it's not a problem because there are LEDs on this wonderful Bluetooth headset in different colors, and they will blink in different color patterns to indicate to you what the current mode of the device is. Now, wait a minute. I'm wearing this Bluetooth headset in my ear, so how am I going to see those LEDs? It doesn't make any sense. This is a horrible design, right? So what this is generally messing with, of course, is visibility, right? We are not seeing the current state of the device clearly because even if I could magically see LEDs blinking behind my ear, blinking LEDs don't tell me much about the current state unless the labeling on the device is super clear. And different colors are usually not explained on the device. They just have to learn the mappings by heart. So it's a terrible case of visibility of current state. And these different lengths of pressing this one button are also things that I cannot see in the interface. It's not visible. I don't see the available actions. I don't see how to get there. So it's the Swedish hairdryer all over. But this is not a Swedish design, just to keep the Swedes out of it this time. So you can see there are all sorts of gulfs that are opening up when I try to get from a goal with this device to actually executing an action sequence successfully. Plus, I will also have trouble deriving the current state and the effects of my actions, but that's the gulf of evaluation that we're going to get into more now. The gulf of evaluation means that, in general, it's often unclear whether a particular action that I wanted to do was actually successful, or if it was successful, what the effect was. The problem here is that we're missing feedback. I promised you would talk more about feedback, and this is where we do this. So, an ideal system in terms of the gulf of evaluation has no gulf of evaluation, right? You would see the system state clearly, visibly, so your eyes or senses, ears, whatever it is, gets a clear signal, a physical signal from the system that tells you, its message. Secondly, you should be able to easily interpret that message into what it means. And finally, it should match the conceptual model that you have of that system and should allow you, therefore, to compare your interpreted result with your goal that you had in mind. Let me give you an example here, and this may make it a little clearer. Let's say you have a printer and you send a print job to that printer, and then you walk over to the printer, right? Let's say it's in a different room. So you walk over to the printer, and it has an indicator light that blinks. Now, there are two situations here. One situation could be that LED is really weak and the printer is standing in a sunny area of an office, and you look at it and you actually cannot tell clearly if that LED is even blinking or not, or if it's on or not, right? Sometimes that happens. So that would be a problem with the very first step of perceiving the result. We couldn't even reliably perceive with our sensors what the signal is. However, let's assume, the room is dimly lit, the light is blinking away happily in green, you can clearly see it, but you have no idea what the heck this means. That's when you run into trouble in that second step, right? You've perceived the result, but you cannot interpret it because you don't know what a blinking green light means. Is the printer out of paper? Is it still busy processing the printing? Should I stay here for a few more minutes? Is it going to print ultimately? Or is it just, hung up on an arrow forever and I'm going to stand here, for 3 days before I realize? I don't know. So in that case, the blinking LED, while it's physically perceivable, is not interpretable. So we fail at that second step, right? And then finally, you might also say, okay, I've seen that message, I've understood that message means the document is printing. But if I wanted to compare to my goal to have the document printed, I'm still struggling because it doesn't tell me how long it's going to blink, right? Is it going to blink is it going to take 3 hours to print, or is it going to take 5 seconds? So we're missing proper feedback about progress, which makes it hard to map it to our original goal just to get that document printed in paper and hold it in our hand. A second example is from a computer game, Myst. It's been around for a long time, but we just checked the other day. There's just been a re-release of it, so we can still say it's a current game. So we're using it because it's a wonderful example. It's an adventure game. You run around on an island. You find levers and switches and buttons. You press them, and apparently nothing happens. But if you pay very close attention and try this out a lot and play the game a lot, you understand that, for example, by pressing like a button near this fountain here, or operating a lever near this fountain, on the other side of the island, a door opens, right? Now, that's a fun game to play, but it's a horrible user interface, right? So we normally don't want our user interfaces to be adventure games, right? We want them to be a little less exciting and a little less challenging. We want to use them easily, effortlessly, without having to go through these guessing games. So what this means is that in Myst, the concept of, thanks, Prince of Persia. Yeah, another classic. Also had some of those levers. The concept of games is often to make the mapping between what you do and its effect in the world, or for you to perceive and interpret that effect, particularly hard, right? Intentionally hard. And that's not good user interface design, but it can be good game design because you want a certain challenge. So we've put this together as the 7 stages of action here. You go from goal to plan, to formulate a plan, to specify an action sequence, to perform that action sequence, to change the environment, and then to perceive with your senses the results, to interpret them appropriately based on semantics, and then to compare them with the result, with the goal that you had in mind originally. One thing to be careful about here is that there are situations in which you may start a complete, 7 stages of action cycle, and you end up not being able to complete the goal, but it may be because you made a mistake along the lines, although you still completed 7 stages. So let's say you wanted to print out your CV, your curriculum vitae, and you send it to the printer, and you go through all these things, and in the end you walk up to the printer and you hold in your hand your latest assignment instead. So you picked a wrong file. You still went through the 7 stages of action for printing, all right, but something went wrong before, right? You picked the wrong document, and that may have been a mistake that you made out of just not paying attention, or it may have been a mistake where the file was labeled wrong, etc., etc. We're actually going to talk about those kinds of mistakes more in the next lecture. What I want to explain is that the 7 stages of actions are really a useful thing to have as a design guideline, because it gives you a basic checklist of questions that you can ask yourself as you design an interface to avoid these different gulfs. First of all, if I look at the interface, does it give me an idea of what I can even accomplish with this thing? Like, what is it for? What does it do? It helps me to map my goal to, oh, I should use this device to achieve this goal. Then, does it offer me the alternative action sequences? Does it tell me what kind of things it can do to formulate a concrete plan to get to my goal state that I want to reach? Then, can I see clearly how to perform these different actions and get to the physical execution of these different actions with the device in an easy way? And once that's happened, I can then ask myself, Does it give me a good way to see visibly or audibly or via haptics or whatever the indicator's channel is? Do my senses get a good chance at picking up the result? Am I getting some kind of feedback that I can perceive? If I do, then I can step up one level and say, okay, once I perceive that, you know, the blinking LED, for example, is it a good explanation of what happens? Can I interpret it well to understand what it means to me? And then finally, can I make the link back to my goal with this feedback and decide whether I've reached my goal or not? So each of these stages will require its own design strategies, but this is a good way to understand why we're telling you about the 7 stages of action. It's not just to, you know, have a model. The model would be useless for us in HCI, in interaction design and usability, if we couldn't use it to derive from it certain questions and processes that we can use to do a better job in designing user interfaces. In summary, for today, to wrap up, we started looking at a bunch of mappings, right? We've seen spatial mappings, perceptual ones, the voodoo principle. We've seen the biological and cultural analogies. Some apply universally for everybody on this planet. Others apply only in particular cultures, and you need to be aware of the differences. Natural mappings are a great way to achieve intuitive usability, right? They take away a lot of the guesswork in using a device, so make use of them if you can. We've then taken a look at constraints. They were sort of the twin brother of affordances, sort of the other side of the coin, if you want, the flip side of the coin. Affordances tell me, and signifiers, what actions are possible and where they can be done, whereas the constraints are there to avoid certain actions, right? And again, these also have different ways of doing that kind of thing, and if they are easily perceivable, then they are actually working, right? If I can't see them, then they can lead me astray. And finally, we've taken a look at the 7 stages of action model here, which is an engineering model, right? It's there for us to help us design better systems. You know, we don't really have these clearly defined processes in our head. You wouldn't be able to clearly delineate those with like neural measurements or anything like that. In fact, they often blur into each other, but it's a way to look at this and give some structure to what people are doing and to use it as a tool to understand where I can help the user to use a device with confidence. The gulfs that can open up in these 7 stages of action are probably the most important thing to keep in mind here, because they are the points where our usability can fail, right? Where our device can actually, or our interface can actually make the user stumble. Alvina, you had your hand up. Is there a question you wanted to ask or a comment?
Yes, I have a question. Basically, so there are 7 stages, right? So it's important that whenever we perform any operation, all of those 7 stages are included. For example, in the stage specify, it was written that to think what can we do, right, to perform something. But I mean, if we are already experienced with something, we always do not think what to do because we already know what do we need to do. So I'm a little confused here, like in any of the operation, all of these stages are included, or sometimes it happens that 1 or 2 are not included.
They're always included. Is a very good question. They're always included, but how you find the answer to these questions will depend on how well you know the device. If it's a new unknown device, you walk up to a printer at a lab that you've never used before, then you will you will consciously think about each of these and look for cues and try to build a first conceptual model because you don't have one yet, right? The first time you encounter a new printer in a lab, you will start building up the conceptual model of how you think this thing works. Where do I insert the paper? Where do I take out my finished print? What do the buttons and the lights mean, right? You build that model. So it's a conscious effort that takes some, some thinking and there's learning happening. if you have a device that you're very comfortable with, like maybe your printer at home that you've had for 3 years, then these things don't take conscious effort anymore. You know that when the printer blinks orange, oh, okay, it's out of paper. It doesn't say so, or it only says so if you walk up to it and look at the the labeling, but you can tell from across the room, right? So it's a very low effort thing for you to do because you've gotten used to the device. And it's important to realize that humans are amazing, right? We put up with the crappiest user interfaces, and ultimately our brain is so good at building models and at understanding things and at learning and at adapting that we can even use really terrible user interfaces. But don't take that as an excuse to build crappy user interfaces, right? Because on our way to mastering this really crappy user interface, there's endless suffering and there's endless thoughts of maybe I should get a different printer. This thing is driving me nuts, right? And so if you manage to design your interface so that, for example, you walk up to a printer and the printer is designed so that it's immediately clear whether it's out of paper, whether it is currently printing, whether it is on, whether it's out of tone, or whether all these things are clearly visible and you have no problem at all understanding how it works, how to refill it, how to pick up your print. That's a wonderful UI, right? Because then you don't have to spend this cognitive effort the first time. And if it's a printer that you only encounter every few weeks or every few months because you only use it occasionally, maybe a printer like in a public space that you go to every few months, then you really want a system there you don't have to relearn it every time you get there, because you're going to have forgotten all that you learned after a few months of not learning it, right? So good interfaces reduce the effort. But to get back to your original question, the 7 stages always happen. It's just how much time and effort we spend on getting from one to the next.
Okay, thank you.
All right. Any other questions? We do have a few minutes that you can ask questions if anything else is unclear. All right. If anything else comes up, feel free to ping us via the usual email channels, and we'll also have the lab, of course, coming up where we will talk about assignments that are related to this kind of stuff. Thanks everybody for listening. We wrapped up a little before our time today. Glad you were here and helped us out and participated in the in-class exercises. I'll see you next time. Oh, Moodle mostly, not email, please. Yes, thank you, Marcel, for that clarification. Moodle it is. All right, thanks everybody, and bye.
This content was provided by RWTH Aachen University.